interacting with organisms. And then, instead of discussing superfluidity, which I believe very important and one of the central issues of the course, important also in connection with the magnetics, theory of magnetism, and theory of superconductivity, which we will have started next week. I will speak about superfluidity on Monday. But today, what we will do in the remaining part of the lecture is basics of some classical theory of magnetism. I spoke with Professor Müller, and he said that in principle you had it in facultative in the problems. So I would like to refresh it for you. It will anyway be repeated when we discuss the quantum version, fully quantum version of local magnetism. I'm speaking now about local magnetism, which we will discuss in great details, also in connection with the theory of phase transitions. Yeah. So this is how the lecture will be organized today. Any questions regarding lecture on Wednesday? Okay. Question?
I assume that the short range interaction, we have to, the two things, it's not negative.
Can you speak a bit louder?
Yeah. About Hamiltonian, you say that for short range interaction, we didn't take the two things is not negative because here we didn't assume the short range interaction.
No, actually, my derivation, basically a whole derivation, didn't assume short-range interaction. What I said then was that in principle, one can proceed with long-range interaction as well. Namely, you remember the way terms, let me again depict it diagrammatically. So this was diagram, generic diagram, which we considered. It describes scattering of two particles, and scattering since they interact. So there are several possibilities, as I said. The first one, which we took into account, was related to the fact that both particles are sitting in the condensate. Then we use notation that the condensate particle is like that. So if all particles are in the condensate, then the transformation of this one is to this one. Then, and it gives us the result 1/2 u node times n node square, because this interaction transfers zero momentum. All particles at k equal to 0. This one after scattering, this one, and this one. Then, as I said, we will consider the processes when one particle is in condensate and another one out of condensate. Two types. For example, it's possible to have process like this, when particle scatters on a particle being in condensate. As a result, this particle comes out of condensate, and this one collapses in condensate. So in these processes, there is a momentum transfer. So since it's a zero momentum, and we have momentum conservation, this then is k, and this is k, and we also have uk here. And there are two types of the processes like that. But in addition to these processes, there is a possibility to scatter when the particle scatters on the particle sitting in the condensate, such a way that the particle remains out of condensate, and this particle remains in the condensate. So here, as you see, it's K, 0, 0, therefore 0 momentum is transferred. So it's U0, U0, which comes here. So you see that these two diagrams are different. When we collected everything and used the fact that the total number of particles in a condensate is not conserving quantity, so we need to express it in terms of the total number of particles in the system, then the correction of the same type comes and cancels this one. So what remains actually is accounting of that type of processes, which assumes that the interaction should not be necessarily short range. When we got a spectrum, EK, which was 4 times beta k hk squared over 2n plus h squared k squared over 2n squared, we discussed two possibilities. First, short-range interaction, and this is quite natural, approximation of particles being not charged, not possessing any magnetic momentum, so they interact only when they collide. Because there is no other source for long-range attraction, like Coulomb interaction or dipole-dipole interaction, if particles are not charged but characterized by dipole momentum and could be polarized. No magnetic momentum, which would create some kind of spin-spin or magneto-dipole interaction, nothing. So then, of course, in this formula, we used that beta k is equal to 1/2 u node times n over v. And then we arrived at the conclusion that there is a Goldstone mode in the system, and the spectrum of the excitations is gapless. However, as an example, I told you that the formula is equally applicable for the situation where we have very long-range interaction, namely Coulomb interaction. So I said, suppose we have charged bosons, characterized by some charge, and if we plug in here not U0, so the formula for U0 short-range interaction I gave you, it is proportional to integral dx x sinus x from 0 to qa. So it somehow oscillates, right? Since there is 1 over q cube here, so it oscillates, and we can find ourselves by small momenta. If the interaction is long range, then the gap appears in the system, especially for the case, well, precisely for the case where the interaction is Coulomb-like. And I just want to draw your attention to the fact that long-range interaction could dramatically change behavior of the system. But I didn't assume it. Actually, all calculations have been done carefully, accounting for both zero momentum transfer and finite momentum transfer. Okay, you can ask me what happens with a zero momentum transfer if we are back and consider this term. So this I didn't tell you, actually. You may ask me, right, okay, if I have uk as 4 times pi e star squared over k squared, this is a Fourier transfer of Coulomb interaction, what should we do with a formally infinite term, which is a constant, dropped from our calculations? Yes, we discussed this question in more detail when we discussed excitations in fermionic systems subject to Coulomb interaction. But the answer on the question what to do with this infinite constant is actually very simple. U system, charge system, has to be put either in positively charged background in order to make system stable and electron neutral, or to consider two-component system. For example, for electron plasma, namely system of charged electrons, we need to have counterpart describing positively charged ions. So it will be two-component electron plasma, but in total the system is neutral. So the total charge of the system is equal to 0. Accounting for conditions of electron neutrality, and I will show it to you in detailed calculation, requires that zero component of potential should be dropped from the system. So actually, and only one point, because it corresponds to the condition that total charge of the system is equal to 0. Therefore, we don't have to care about this constant anymore. One point of interaction is anyway dropped out, but we have to be careful here. I mean, and here we see that the answer is correct. It is not 0 Fourier component, but finite k Fourier component. So therefore, the treatment of charged Bose gas was done correctly, and 0 Fourier component disappears from the calculation due to global condition of electron neutrality. Okay, did I answer your question? Okay, let's then see some slides. Okay, I will keep it that way. So, what shall we? First of all, these are two gentlemen being the pioneer in discovery of new phenomena, new quantum state of matter, which is Bose-Einstein condensation. And here you see, historically, I told you that the theoretical prediction was done in middle of 20th, and there was interest, and there was a constant attempt to find experimental realization of Bose-Einstein condensation, which was not very successful due to the reasons again which I mentioned to you, namely hydrogen was not so good because of tendency to create molecules which then solidify and form solid state where there is no room to Bose-Einstein condensation. Helium was too much interacting, namely at extremely small temperatures, much smaller than transition to condensate. It was shown that only 10% or a bit less than 10% particles stay in condensate, so the theory of weakly interacting gas is not applicable. The attempts to see condensation of excitons, bound states of electron holes, which is also boson, a neutral boson, in semiconductors was also not very successful, again due to the reason that any kind of bound state, electron and hole, is not true boson. It's a composite particle which doesn't behave like bosons at short distances. Of course, you may argue that there was a superconductivity, which is in some sense a superfluid state of Cooper pairs, what we will start learning next week. But you will see that in theory of superconductors, Cooper pairs can hardly be characterized as bosons because they are strongly overlapping. So the size of such kind of bound state, and this is truly not a bound state, this is a connective state, is much larger compared to the mean distance between Cooper pairs. Therefore, Cooper pairs cannot be seen as isolated objects, which we would very like to have in our theory, namely to have a situation when the size of bosons, whatever it is monolith or composite, should be much smaller compared to the distance between bosons. Then, of course, we can speak about particles. However, in 1995, the Nobel Prize was given for the discovery of Bose condensation in alkali metals, And since that time, you see that the growth of publication on this topic increases very much. So this is Nobel Prize. In '95 it was discovered, and Nobel Prize was given in 2001 to Eric Cornell, Wolfgang Ketterle, and Carl Wieman for achievement of Bose-Einstein condensation in dilute gases of alkali metals. Again, I would like to show you this nice cartoon, which demonstrate you, first of all, how quantum states are different from classical one, and how fermions are different from bosons. So in this slide, what we see, we take three identical but classically distinguishable particles, which means that we can associate color with them, green, blue, and red, and we try to put these particles on the levels using possible combinations. So namely, there is only one state when all three particles sit on state 1. So the constraint which we use here, that the total energy should be equal to, should be a constant. Namely, since levels are assumed to be equidistant in this model, to have energy equal to 3, I think we can have either all three particles at energy level 1, or two particles at energy 0, one particle at level 3, or all these combinations. So you see how big the fraction of particles, how big is fraction of the state where three particles occupy a single state. Coming to quantum mechanics, what we have to do is to make these particles indistinguishable. So for indistinguishable particle, there are two possibilities. There are two statistics, either fermionic or bosonic. So you see that if we consider bosons, then this is what we get compared to classical occupation numbers. However, if we consider fermions, there is a Pauli principle, and there is only one possible state. Therefore, there is no possibility for triple occupation, and we can conclude that although for classical probability of triple occupation is triple, for bosons it's 10%, for bosons it's 33%, for fermions it's 0, and bosons like to get together, or as you heard on yesterday's colloquium, if you were present, bosons like students, to say, rephrasing the sentence of the speaker. Okay, so then I'm repeating briefly what we have discussed in the lectures, two lectures devoted to Bose condensation. And Fermi statistics, you see that basically symmetry leads to two possible statistics, namely Fermi-Dirac statistics when one has a plus sign and Bose sign, statistics where there is a plus minus, which are dramatically different, but both statistics lead to classical Maxwell-Boltzmann statistics in the limit that the average occupation number is much smaller than 1. Okay, this summarizes us our calculations on the thermodynamics. We have found that the number of particles in the condensate is related to total number of particles this way, where Tc is the critical temperature, after which the chemical potential is equal to 0, and it leads to this type of thermodynamics. And especially interesting observation is that the pressure is not dependent on the volume, and the reason that the pressure is not dependent on the volume is, as we discussed, that the number of particles in and out of condensate is not conserved separately, so there are processes back and forth, and only particles out of condensate contribute to the pressure in the system, if we start to change the volume, more and more particles collapse into the condensate, and therefore our pressure remains independent on volume. So changing your box, you just increase the fraction of particles sitting in condensate, and nothing more. Okay, this tells us that the condensation is a phase transition because there is a critical point, and one can associate the order parameter, which we also discussed briefly, which is 0 to the right-hand side from the critical temperature and non-zero to the left-hand side. So it's a typical phase transition. And if we address a question, what happens, what kind of phase transition it is, based on Landau-Ehrenfest classification of the phase transition, and I recall you that this classification actually tells us that the order of phase transition is defined by the order of derivative which possesses jump, derivative of thermodynamic potential, and for example, for first order phase transition, while the thermodynamic potential themselves are continuous function of parameters. Anyway, for first order phase transition, entropy has a jump and specific heat diverges. For second order phase transition, entropy has a kink, it's continuous, but specific heat has a jump, and derivative of specific heat diverges. For this kind of transition, both entropy and specific heat are continuous. The derivative of specific heat has a jump, and the second derivative of specific heat diverges. Therefore, in accordance with the Landau-Ehrenfest classification, it would be called third order phase transition. Let me be back to the formula written here and give a comment associated with our last discussion the day before yesterday. So I showed you with simple arguments that the condensation cannot be achieved in low-dimensional systems at any final temperature. Namely, I told you that for a situation where condensation occurs with a system characterized by short-range interaction, the fluctuations lead to divergence of total number of particles logarithmical divergence for two-dimensional system, and linear with the size of system divergence for one-dimensional system. And this actually tells us that the fluctuations in low-dimensional system are strong, so strong to destroy the coherent state, the quantum fluctuation. You may ask me, how about experiments? I mentioned that experiments, and I will speak about it a little bit more now, can show us existence of condensate in quasi-two-dimensional structures. So what one has to keep in mind, this formula. This formula is obtained for box, namely for potential that the particles are non-interacting within the box of the size L, and they cannot go out of the box at all. However, the experiments to trap atoms are done in magneto-optical trap. Magnetic-optical trap forms some special form of confinement potential, which is in most cases is parabolic. In parabolic potentials, you know, harmonic oscillator, then particles, that there is a zero-point motion, particle will condense not in a state with zero energy, which is here and which is not accessible, but on the state with the lowest possible energy, which is half of frequency characterized by this trap. Actually, for trap, for confinement potential, parabolic potential, this formula should be revised, actually. And if you do calculations correctly for particles in parabolic trap, you will see that the number of particles sitting in condensate is proportional to total number of particles in the system, but the power here will not be 3/2 for as it is for three-dimensional box, but 3 as for three-dimensional magneto-optical trap. And then you may also see, and I will give it to you as an exercise for homework, that the condition of theorem, which I told you, namely existence of Bose condensate, is not applicable anymore in the trap system, because I didn't say anything about confining potential, and confining potential actually stabilizes condensation in low-dimensional systems. Okay, this is what we discussed the day before yesterday, namely that if the particles are interacting very weakly, namely they only talk to each other when they collide, then we can simplify our, first of all, we can diagonalize our Hamiltonian in the case where this condition is applied, and when the gas parameter is small, and diagonalizing Hamiltonian, we see, first of all, that there is a linear branch of the excitation for small momenta. And, as I said, not all particles are sitting in the condensate, so interaction kicks out particles from the condensate. This is what interaction does. And now, let's discuss one more time the physics of the condensation, and I would like to remind you that there is a big similarity between what happens in lasers and what happens in condensation, because what we see here, that the ordinary light which comes from this lamp is incoherent, consists of many small waves, many modes, while the laser beam represents diffraction limited, coherent, and one big wave. So this is coherent signal, monochromatic, single mode. So this is the similarity with the gas, that in ordinary gas, above the temperature of condensation, of course, the Broglie wavelength, and you remember that in accordance with quantum mechanics, there is a corpuscular particle dualism saying that the wave function solution of Schrödinger equation can be interpreted both as a particle and as a wave, and the particle interpretation holds when the de Broglie wavelength characterizing the wave package is much smaller compared to the mean distance. So for ordinary gas, we see that this is precisely the case. We can speak about gas of bosons, quantum particles. So it's the same way, incoherent, consisting of many small waves and many modes. While the condensation represents a state of matter characterized by single wave function. So like a laser beam, we have coherent one big wave monochromatic description of the quantum. This I already said you before, emphasizing the difficulties in observation of Bose condensation in ordinary systems like hydrogen, excitons, and helium. Indeed, it was very surprising that people doing quantum optics discovered this Bose condensation in alkali metals, and it was absolutely not anticipated by the community. So, what has been done? And what kind of experiments were pioneered experimental discovery of the Bose condensation? So this was a gas in magneto-optical trap of form close to parabolic, and what people did, they trapped the gas in this potential, and then at some moment they release the potential and discover and studied time of flight experiments saying how the velocity or momenta are distributed in the system, depending on the temperature of the system. Of course, in the first experiments, the number of atoms trapped in the such kind of potential was not very large. So it was not 10 to the power 23, but rather 10 to the 6, 10 to the 7, which means that the fluctuations of this system, which is 1 over square root of n, are not really small. However, with improving experimental technique, it was possible to do experiment with much larger number of particles. And what we see here, this Bose-Einstein condensation in Gila with rubidium done in 1995, that for temperature larger than Tc, the time of flight experiment is dramatically different from the experiments at temperature much smaller than Tc. Here we have peak corresponding to zero velocity or zero momentum, which actually is manifestation of Bose condensation. When you think about Bose condensation, of course, you don't think about condensation like water, which condenses on the glass when the rain comes, but it's a condensation in momentum space. So this is a momentum distribution, and therefore the peak corresponding to zero momentum means that there is a big number of particles, and the height of this peak is proportional to number of particles, is occupying quantum state characterized by zero momentum. So this is what I said. The first experiments were done with rubidium, sodium, and then later with lithium, potassium. And the first experiments contained 10 to the 6 particles with a critical temperature of 1 microkelvin. You can imagine how low the temperature is, but basically you may ask me a question, what's the meaning of this temperature? And the meaning is very simple. The meaning is the temperature is kinetic energy of particles. So if particles are extremely slow, and this was a reason in motivation of this experiment, is just make these particles so slow that the temperature is very low and the particles can condense. This actually shows the pictures from two different experiments. The first one was really very poor in the sense that the number of particles was 10 to the power 3, but at the end of the day, as I said, the improvement of technique was very big, and the community was convinced that it is in fact Bose-Einstein condensation, which opened a lot of new directions in physics of ultra-cold gases, molecules. Yeah. So this is a summary of what happens with gas when you low down the temperature. So you see that more quantum behavior in the system occurs. One can speak about de Broglie wavelength and characterize system in terms of it. At the critical temperature, the de Broglie wavelength becomes comparable with the mean distance between particles, while for zero temperature, we have a giant matter wave which characterizes the Bose condensation. So for non-interacting system, all particles are in condensate. For weakly interacting systems, there are almost all particles in the condensate, and the condensate is a classical state which can be characterized as single wave function. And this last transparent summarizes some possible application of Bose-Einstein condensation in many body physics, in discussion of superfluidity, in metrology, atomic clocks, and matter wave sensor, in studying of collision and corresponding chemistry, in quantum optics, creation of atomic laser, and also in nanotechnology, while Bose condensation, also called atomic chip, is also a rapidly growing field of studying both experimentally and theoretically. And here you see that experimental facility, actually, and fantastic experimental facilities, drive, so to say, or force theorists about to think about something which was impossible, which sounded like science fiction before. So now the temperatures of the scale of picokelvin are possible. The experiments for crossover between Bose-Einstein condensation and superconductivity are possible. The construction of optical lattices opens a direction which people cannot dream before. Namely, instead of studying the Hamiltonians describing approximately the strongly correlated systems and solid states and building up very powerful computers which will allow to perform a calculation, approximately calculations with the optical lattices. One can model the Hamiltonian and actually do a measurement. And this measurement will be equivalent to the calculations. And moreover, in optical lattices, since the distance between particles is controllable by wavelengths of the laser and can be as big as 1,000 angstrom, which can never be achieved in solid state. You know that the typical lattice constant in a crystal is of the order of 5 angstrom. So putting particles aside of each other means we can control interaction and make system really ideal. So the ideology of optical lattices now opens the possibility to measure the properties, namely measure correlation functions, which would be exact in the sense that everything is tunable and controllable. Okay, that's all what I wanted to show you about nowadays experiment. I believe it is important for you to fill in what's going on in the field, and that you are here not to discuss physics of 19th century, which of course also very interesting, and not physics which is 50, 70 years old, but we are discussing something which is applicable in nowadays research and which is very rapidly growing an interesting field and a direction of research today. Okay, so that's all with that. Now we continue our lecture. Any questions, by the way? So actually you are born in the right time, in a sense. You will see the progress and you will see the achievement and development of modern science, which is just developing in front of you, so to say. And moreover, you have all chances to participate in this development and put your own contribution. That's really fantastic opportunity for everybody. Okay. So today we start a discussion of local magnetism. And you will see that actually the logic of the course is to emphasize the deep connections between the different parts of many body physics, magnetism is definitely one of the examples of many-body physics, you should try yourself to see the analogies. The possibility to see these analogies is very important quality of researcher. The more analogies you see, the better understanding of physics you have. And I will try to emphasize as much as possible, and whenever it is possible, what are the analogies between fields which look like completely different from the first glance. For example, we will see that there is very strong similarity between description of superfluid systems like weakly interacting Bose-gas and description of antiferromagnets, for example. Systems characterized by local moments in two sublattice setups. Okay, we have already discussed a little bit the magnetism of electronic system, which was a magnetism of itinerant structures. So the structures where electrons were mobile. Although you might have had the impression that the magnetism, and we discussed already diamagnetism and paramagnetism, was a kind of single particle effect. Because we didn't say anything about interaction, and interaction never appeared in our theory. However, this naive conclusion would be wrong. Why? Because the magnetism of electronic system was studied in the presence of the Fermi sea. And Fermi sea is already collective effect. You see that fermions behave such a way that there is no classical analogy with them. There is no classical analogy of Pauli principle. So the fact that only one or zero particles can occupy quantum state is already taken into account many-body effects, statistical effects, so to say, effects associated with Fermi-Dirac statistics. An existence of this Fermi energy, which is the energy scale for fermionic system, resulted in the fact that we can have in the system of mobile electron either susceptibility positive or negative, constant, which means that the response on applied magnetic field can be directed as along the field with the same direction or along the field with the opposite direction. So one effect is known as a paramagnetism. Magnetization induced by applied magnetic field is proportional to magnetic field itself. And positive or diamagnetism, where orbital motion creates a counter field, and magnetization in the system is induced by magnetic field, is also proportional to magnetic field, but has a negative sign. So if we speak about magnetism, and would like to give some classification of possible types of magnetism, then probably the first way to separate this kind of magnetism would be itinerant magnetism. Itinerant means that the electrons which are responsible for magnetism are mobile electrons which can move, and localized magnetism. So today we start discussion this localized magnetism. And what does it mean, a localized magnetism? Suppose you have a crystalline lattice and you have elements characterized by internal spin or orbital moments. So the inner shells, for example, of such atoms is not completely filled, as it is for noble gases, for example, but filled only partially. And you know from basics of quantum mechanics that the way electrons occupy the orbitals is subject to Hund rule, namely first all orbitals are occupied by a single occupancy, namely the total momentum is maximum, and only then you start to put particles with the opposite spin into the same orbital, since at least one quantum number has to be different, and then when the shell is completely filled, you again come to the situation with a zero spin system. However, for many elements, we don't have completely filled orbitals. Therefore, we can think about magnetic moments sitting in the position of atoms, and magnetization in such kind of system can spontaneously occur. Namely, the sample can be characterized by total magnetic moment or total magnetization, and this is what we know from our everyday experience, that piece of metal can attract another piece of metal, and this is what we call magnetism, known to Chinese for millenniums, but the nature of this magnetism, as I said, is related to the existence of local moments. Local means that in contrast to itinerant system, where you have orbital motion of electrons, these moments are not moving. They are sitting in the position of atoms and do not possess any kind of kinetic energy. Unlike itinerant system, where everything is associated with kinetic energy, interaction is negligible. For localized system, everything is associated with potential energy. Okay, to give you more example of magnetism, I would like to stress that for local system, for example, there is a possibility to have more exotic version. So this one says that all magnetic moments are aligned. So what happened then? This is a critical phenomenon. We can speak about it as a phase transition. And as an other parameter, we choose magnetization, average magnetization as a function of temperature. So what we see that above some critical temperature, we have a state paramagnetic, in the sense that here susceptibility, here the magnetization can be tuned by applied magnetic field, and in zero magnetic field, magnetization is zero, similar to what happens in paramagnet in itinerant system. However, below critical temperature, the system can be characterized by spontaneous magnetization, like in the magnet in this piece of iron, and this spontaneous magnetization as a function of temperature reaches its maximum value at zero temperature. So, as we discussed in the course of advanced statistical physics, this is a typical example of second order phase transition associated with the spontaneous symmetry breaking, and what is broken here is rotational symmetry. So, what kind of rotational symmetry? If we look at single spin, it can be viewed as, of course, it's quantum operator, and it's quantum operator subject to non-commuting algebra. However, suppose that this momentum is large. We can speak about it semi-classically. Then we can think about it as vector living on a sphere, and in the absence of magnetic field, actually all directions of characterizing this vector is equivalent, which is the same as to say that the vector is freely rotating on a sphere. Since we speak about system of spins in a crystal, therefore we of course need to speak about interaction between these spins. But if the temperature is high, this interaction doesn't play so important role, and above critical temperature we have this parameter. Below critical temperature, the system wants to be magnetized, namely all momentums want to be aligned in one direction, and this is typical ferromagnet. So what we do today, we consider this classical version of theory. We consider simplest possible Hamiltonian of the classical momentum subject to magnetic field. No interaction whatsoever between neighboring spins for the moment. We calculate partition function of this system. We calculate magnetization in the system. We calculate susceptibility. And then we come to the concept of, so to say, molecular field, how to include other spins in very simple way, and construct very simple semi-classical theory of magnetism. And as I said, I know that you did something with Professor Müller. It will be repetition, which is necessary for me to make a bridge between semi-classical theory of magnetism and quantum theory of magnetism, fully quantum theory of magnetism. Of course, when we discussed itinerant magnetism, I already explained to you that the magnetism is a quantum phenomenon. Either if it is related to itinerant motion, when you remember we had the effect associated with existence of Fermi sphere, which is a quantum phenomenon, or with a localized magnetism, where, as I said, the magnetism is related to existence of spin in the system, and spin is intrinsically quantum number. But saying more about localized magnets, I would like to mention a possibility to have two sublattices, for example, A and B, and possibility to have different alignment of spins on sublattices A and B, such a way that relative alignment is antiparallel. So the system, which are characterized by zero uniform magnetization, so if we plot what's magnetization, what's magnetic moment in the system it is zero. However, the uniform magnetization, which is a response to uniform magnetic field, should be contrasted to response on staggered magnetic field. Suppose we have a magnetic field which is modulated in space the same way. Then the response to this staggered field, which is called staggered magnetization, and is characterized by a wave vector which is inversely proportional to lattice distance between sublattices A and B, lattice spacing. This staggered magnetization will also be non-zero and can be considered as a order parameter. So both ferromagnetic systems and antiferromagnetic systems are example of second order phase transition, where order parameters are either uniform magnetization or staggered magnetization. We will learn, and I presented to you with the details, that if we ask a question, what are the excitations in the system, both, say, in ferromagnets and antiferromagnets, the answer will be, of course, different. For ferromagnets, the excitations associated with the possibility to rotate very little at low temperatures around the direction of uniform magnetization, and these excitations are called magnons or spin waves, are characterized by quadratic gapless and quadratic dependence of the energy as a function of the momentum. This is the subject of Goldstone theorem. We discussed it, that the excitations are gapless, and also there is no long-range order in such systems, so the fluctuations will kill long-range order of that sort in low-dimensional systems. Namely, if the interaction between spins is short range, then the theorem forbids us to have ordered state in two-dimensional structures, except zero temperature and any order in one-dimensional structures. You see the similarity between you will see the similarity between ferromagnets and ideal Bose gas, which is also characterized by this spectrum. So it mimics free particles, while lambda, of course, its spin stiffness in the system has nothing to do with real mass. Just dependence of energy as a function of the momentum in a ferromagnet is very much alike to ideal Bose gas. For antiferromagnets, we will see that the difference is dramatically different. So epsilon P is Cp, and therefore we will see that the similarity between antiferromagnets and weakly interacting Bose gas is indeed present. So we discussed in details the thermodynamics of both systems and discussed a way how to diagonalize the local Hamiltonian, which I am not writing now, and how to get these new quasi-particles, which are magnets. But before I proceed with the simple calculations for Langevin function, let me give you a few more examples, just in order to convince you that it's not all what we have in a variety of magnetic systems. We can have many other possibilities. For example, the momentums on two sublattices can be different, and this is known as a ferrimagnet. Regardless whether they are parallel or anti-parallel, there is no anti-ferrimagnets terminologically. There are also frustrated systems where one cannot align spins. Typical example is triangular lattices. Suppose we want to align spins in triangular lattices parallel. This is fine. So ferromagnetic state is consistent with this. However, if we would like to align three spins anti-parallel, then we are in trouble, because if we start with this pair, these two spins want to be anti-parallel, and that's fine. This is the same for this pair, but for this link, it doesn't work. So the system is so-called frustrated, because this spin doesn't know where to look. And resolution of this paradox will be resulted in the alignment of spin of that way, so they will rotate, creating optimal angle, which is 2 pi over 3. But this is typical example of a magnet in a frustrated system, which is again a very rapidly growing field nowadays, especially in application in spintronics, in nano devices, in order to make, at the end of the day, the hardware for quantum computing. Okay, and there are so-called spin glasses, where the system is frozen, so to say, and the metastable frozen state is very long living, like the glasses in the window, which you know is also metastable state, but the lifetime of this state is huge. There are, of course, other possibilities to have itinerant magnetism, like spin density waves, which is itinerant analogous of antiferromagnets, which does exist in itinerant system. In many aspects, these spin density waves